Heat of Reaction, The Combustion of Magnesium by Maggie Palis and Hannah McDonald.
The purpose of this experiment is to apply Hess's law to a practical scenario and to utilize learned thermochemistry applications in order to draw conclusions.
This process is an example of an application of thermochemistry, such as one that might be used by chemists to draw practical conclusions about processes such as their heat of reaction.
This experiment utilizes many thermochemical equations and science skills. The first is Hess's law. It states that the enthalpy of a reaction is equivalent to the sum of the enthalpies of its steps. We also use the equation that states that the enthalpy change of a reaction is equal to the heat of formation of its products less that of its reactants. Finally, we used the heat of reaction is equal to the mass of the system times the specific heat times the change in temperature, or Q equals mCp delta T.
For the first experiment, measure 50 milliliters of 1 molar hydrochloric acid and pour it into a coffee cup calorimeter that has been placed in a beaker. Measure 1 gram of magnesium oxide. Next, record the initial temperature of the hydrochloric acid in the calorimeter, in this case 20.7 degrees Celsius. Pour the magnesium oxide into the calorimeter and observe as the reaction occurs. Be sure to watch as the temperature increases and record the highest temperature. In this case, the highest temperature is 30.1 degrees Celsius.
For the next reaction, measure and pour another 50 milliliters of hydrochloric acid. Obtain 3.5 centimeters of magnesium ribbon. Once again, record the initial temperature. Pour the magnesium into the calorimeter, observe the temperature change, and record the highest temperature. In this experiment, we can see hydrogen gas being released from the calorimeter as the reaction occurs. The highest temperature in this experiment was 24.6 degrees Celsius.
This experiment provides 4 reactions. Through Hess's law, reactions 2, 3, and 4 can be combined to form reaction 1. At this time, we need to calculate the theoretical enthalpy of reaction 1 based on our Hess's law calculation so that we can evaluate accurately the accuracy of the experiment that we have completed in performing reactions 2 and 3. In order to create reaction 1 from reactions 2, 3, and 4, we need to flip reaction 2 and do nothing to the other 2. In order to complete the process of Hess's law, we need to rewrite the 3 latter equations utilizing the now manipulated reaction 2. At that point, we can cancel out all of the repeated species until we reach our original equation.
Next, we need to calculate the theoretical enthalpies of the completed reactions by using the heat of formation for each of the species given, and then subtracting the heat of formation of the reactants from those of the products, in order to calculate the theoretical enthalpies of the reaction itself. We complete the same process for reaction 3, which is made easier in this case due to the pure magnesium ribbon and the diatomic hydrogen, which both have heat of formations of 0.
At this point, we add the theoretical enthalpies calculated for each of the reactions. We utilize the fact that during our Hess's law process, we flipped equation 2 and therefore changed the sign to a positive one. When we add together the theoretical enthalpies of all 3 equations, including the given enthalpy of equation 4, we reach the theoretical enthalpy of reaction 1.
In order to calculate the experimental enthalpies of the reactions, we need to find the temperature change from both reactions during the experiment.
We've calculated the temperature change found in each experiment. We can use Q equals mCp delta T to find the value of the experimental enthalpy. We multiply the entire mass of the system by the specific heat of water by the temperature change. Since the temperature went up in the calorimeter, we know that the experiment was exothermic, and therefore we need to use a negative value for the heat. We also need to convert the value, which comes out in joules, to kilojoules. Next, we calculate the per mole experimental enthalpy by taking the mole values of the limiting reactants for each reaction and comparing them in a ratio to the calculated experimental heat release values that we found for each reaction. Now that we found the experimental enthalpy values, we once again use our Hess's law manipulation to change the sign of equation 2 and then add together equation 3's experimental enthalpy and the given enthalpy of equation 4 to reach the experimental kilojoules per mole enthalpy of reaction 1.
Finally, we find the percent error by subtracting the experimental enthalpy from the theoretical enthalpy and dividing the difference by the theoretical. In conclusion, we found reasonably accurate data to support thermochemical equations We were also able to practically apply knowledge learned in the classroom and understand the impact of Hess's law and thermodynamic concepts in the world of chemistry today.
Since the calorimeter used in this experiment was a simple coffee cup, it is quite possible that much of the heat was lost to the environment, and therefore the calculated experimental enthalpy would be less because less heat would have been recorded. Further, it is possible, especially in the case of magnesium oxide, that remnants of the limiting reactant were left in the weighboat, thereby lowering the experimental enthalpy by overcompensating for the heat released per unit mass.